Let's look at different vector operations for vectors given to me in this ij format. Let's suppose I have two vectors, v is equal to ai plus bj, and w is equal to ci plus dj, where a, b, c, and d are real numbers. In this case, v plus w would be a plus c times I plus b plus d times j. We add the I components and we add the j components. Similarly, if I were to subtract, I would subtract the I components to get a minus ci, and subtract the j components to get b minus dj. Let's consider these two vectors here, 5i plus 4j and 6i minus 9j. If I want to add these, I'm going to add the numbers in front of I, which are 5 plus 6, and the numbers in front of j, which is 4 and negative 9. 5 plus 6 is 11, and 4 minus 9 is negative 5. So we end up with 11i minus 5j. If I want to subtract them and do v minus w, I would subtract the I numbers, so 5 minus 6, plus subtract the j numbers, 4 minus negative 9. 5 minus 6 is negative 1. 4 plus 9 is 13, so I end up with negative I plus 13j. Let's once again consider an arbitrary vector v equal to ai plus bj, where a and b are real numbers. We can also multiply a vector by a scalar, k. And this results in multiplying each one of its components by k, so ka times I plus kb times j. Let's once again look at our vector v equal to 5i plus 4j. If I want to find 6 times v, I would do 6 times 5, which is 30, times I, plus 6 times 4, which is 24, times j. If I wanted to do negative 3v, I would do negative 3 times 5, which is negative 15, I, and negative 3 times 4 is negative 12, times j. I can also combine this idea of scalar multiplication and addition or subtraction. Let's suppose I wanted to find 4v minus 2w. Let's start with 4v. This would be 4 times 5 is 20, and 4 times 4 is 16. So 20i plus 16j. If I multiply by 20, if I multiply by 2, 6 times 2 is 12i, and 2 times 9 is going to make this minus 18j. We can then subtract 20 minus 12i and 16 minus negative 18j to get our final result of 8i plus 34j. There is one very important vector that we should point out, which is the 0 vector. It's denoted by 0 with an arrow over it. And this is 0i plus 0j. It is the magnitude 0 vector. And it is the only magnitude 0 vector that we have. Let's look at some of our basic properties of these operations. The first says that u plus v is equal to v plus u. Addition of vectors is commutative. The next one, u plus v plus w is equal to u plus v plus w. I can switch parentheses around with addition of vectors. So addition is also going to be associative. I have that u plus the 0 vector is equal to 0 plus u, which is equal to u. So the 0 vector does behave exactly like 0 does in the real numbers. We also have that u plus negative u, adding a vector and its negative, this is the same thing as negative u plus u, is going to be equal to the 0 vector. So adding a number and its negative works exactly the same as adding a vector and its negative. My next one says that CD times u is equal to c times du. So this says that scalar multiplication is associative. It doesn't matter what order I multiply the scalars in. My next one says that c times u plus v is equal to cu plus cv. I can distribute a scalar into a sum of vectors. Similarly, we have that c plus d times u is equal to cu plus du. I can also distribute a vector through a sum of scalars. I have that 1 times any vector is just equal to that vector. So multiplying by 1 behaves exactly the way we would expect, as well as multiplying by 0. Multiplying a vector by 0 gives me the 0 vector. Finally, the length of multiplying a vector by a scalar is the absolute value of that scalar times the magnitude of v.